Hello, my name is Satanas. I'm senior software engineer at Intel, and today I'm going to demonstrate a new way to simplify the workload deployment process inside Kubernetes. In classical Kubernetes, we have to define our workload deployments with a lot of properties which are not directly related to our workload objectives. Those include defining resources, choosing instance types, operation system, and many other aspects. We propose a new approach where orchestration is driven by intents, or in other words, objectives for our workloads. The objectives are used by a framework which abstracts away the process of configuring all underlying resources and makes the interaction with the system as simple as pushing a button in the car to switch driving mode. Here, we see an example where on the left we specify a workload and its configuration in terms of resources, such as number of cores, cache, CPU shares. On the right, we see our new approach, where we have a set of objectives for our workload, such as P99 latency, availability, and throughput. In this case, we are not defining exact resources which we want to use, but we are just defining our service KPIs. Resources are then being allocated, managed automatically by our framework to fulfill the KPIs. Our framework is implemented as a Kubernetes operator where the objectives are defined as custom resources, and those are being processed by a planning component. The planning component continuously watches the current state of our KPIs and the system telemetry. The data is used to generate a new action plan which helps us reach the desired state. The actions are realized through actuators interacting with the certain resources. We can accumulate all data in knowledge base, which allows us to take better decisions over time. Our framework can be extended in two specific points. One possibility is to extend it on the actuator side by writing a new plugin for some new type of resource. The plugin can be registered on the fly inside our planning component. Another extension point will be the actual planning. The default planner uses an A-star search algorithm to find a path to our desired state. A planning plugin can enable other machine learning algorithms and combine them for different workloads. To illustrate this in actual example, let's take a look on planning sequence for a real workload. As first step, the user specified the desired target of P95 latency from 400 milliseconds. Looking at the bottom row of our event table, we see that the current KPI state of the workload is 490 milliseconds. We also achieve a throughput of 25 requests per second. So the current latency was not fulfilling our KPI, and the system decides to scale out. This action was actually determined by evaluating our machine learning model and finding a state which gets close to the desired target. After some time, we reached our target and the latency got below the prescribed KPI of 400 milliseconds. No further actions were taken. Due to external factors, it could happen that the microservice configuration which was found is not fulfilling future KPIs. In this case, the planner triggers a new scale-out action to fix this. This approach can be applied with any kind of resources. We can use it also to control certain performance-related characteristic of workloads which we'd like to protect through secure enclaves. In our demo, we will demonstrate that with two tenants, a blue non-secure tenant and a red secure tenant. Both workloads have their own targets and knowledge bases. For the secure tenant, we can use intent-driven orchestration to tweak the cipher secure enclaves automatically. This will have an actual performance impact, and it will help us to reach KPI targets faster. Now I'm going to show intent-driven orchestration in action. We start by looking into our two workloads and their KPI targets. The blue workload, the unencrypted case, is shown on the left console, and the encrypted case, the red workload, is shown on the right. Let's look into the non-encrypted case. We have a function called function deployment, and we define a P95 latency objective of 300 milliseconds. For the red workload, we have a P95 latency of 400 milliseconds. Now we start our workloads and we see the data coming into our user interface. On the left side, we see the state history for both workloads. On the top table, we observe our unencrypted workload. Initially, the workload recorded a latency of 1250 milliseconds. In this case, the planner triggered a scale out action with a factor of 1, which tells us that we have to add one pod to our deployment. Similar event table is provided for the second workload. Over time, the latency of both workloads starts to drop. On the right-hand side, we see two plots. The first one on the left is the number of containers for a given time step. We can see that our encrypted workload, shown with red line, reached 5 containers, and the latency got very close to our target of 400 milliseconds. On the right side, we have the latency plot. Over the time, the latencies are starting to converge to our targets. After a certain point, our planner started accumulating enough data to create a machine learning model. Usually, we need around 10 sampling points to get first results. Let's take a look of the non-encrypted case. We have a 3D function, 3D space, defined by throughput, number of pods, and latency. We use this 3D space to make future predictions of actions which can help us fulfill the desired objectives. And so, after some time, we see our blue and red latency lines converging very close to the desired target, showed in yellow line on the plot. The targets were 300 and 400 milliseconds. As next, we would like to change the target latency for the blue workload. We increase that to 1000 milliseconds. After adjusting the latency, the planner registered that adjustment and starts acting on the new requirement. It triggers actuators and starts removing pods responsible for handling the request for non-encrypted workload. After several time steps, our number of containers dropped to 1 container, and our latency got very close to the desired latency of 1007 milliseconds. We see also that our machine learning models got expanded with further data points, and this helps us have a better prediction. Last but not least, we are looking forward to get more feedback about our approach for intent-driven orchestration and our objective API. We are also very interested to get input on what future actuators would make sense, and if this can be a good fit for your use cases in practice. Please check our GitHub, and we are looking forward to your feedback.